Phew. Whee!
Boing, boing.
Whee! Okay, more of the same. This is going to be questions 6 to 10. So look at the question, have a go, and then I'll go through the answer. So question 6. What is the typical weight of an empty single-decker school bus? What do you think? Okay, so we're talking about weight here. Weight equals mass times gravitational field strength. Gravitational field strength is approximately 10 newtons per kilogram, and that's a constant. So really this is a task where we have to estimate a sensible mass. I know that a small car is approximately 1,000 kilograms, 1 metric ton, and an empty single-decker school bus, or how many cars would that be? I think it's going to be about maybe 10 cars. So let's just plump that into the equation and see what we get. Okay, let's imagine that a small car, 1,000 kilograms, small bus, going to be about 10 times that, so it's 10,000 kilograms. The weight of a small bus, therefore, would be mass 10,000 times my gravitational field strength 10. So my estimate would be about 100,000 newtons. Okay, I mean, I don't know, it's an estimate. So let's have a look at the answers and see what we've got. So A, that's just way too small. B, 12,000 newtons, that's more pretty much what the weight of my small car would be. If I multiplied it by 10, I'd get 10,000. So that's not enough. C is close, and D is just too big. So C, 120,000 newtons. Okay, this question really is just asking, do you have an understanding of what mass is really, how much mass is, what does that mean? So if you remember that a small car is approximately 1,000 kilograms, that kind of gives you an idea. This is one of those questions where you're kind of trying to make a sensible guess. Okay. Okay, question 7. How was the sun formed? From dust and gas pushed together by gravity leading to fission, pulled together by gravity leading to fusion, or pushed together leading to fusion, or pulled together leading to fission. 4 options, A, B, C, or D. Okay, so we're starting off with dust and gas. Okay, pushed together by gravity or pulled together by gravity? What makes the most sense? Well, gravity is basically mass being attracted to mass. It's a non-contact force. Gravity is a pulling force. Okay, so we're looking for B or D, because the other two are pushing forces, and we need to know that gravity pulls those dust particles together until there is enough temperature and pressure to sustain fusion. That's the joining together of two small nuclei into a larger nuclei. Isotopes of hydrogen fuse or join together to make a nucleus of helium. So it is going to be a pulling force that leads to fusion. Pulled together by gravity leading to fusion is B. Okay, question 8. An element has more than one isotope. which currently describes the atoms of all isotopes of this element. A, B, C, or D. What do you think? Okay, well, what is an isotope? An isotope is when we've got the same element but different neutrons, different number of neutrons. Okay, by same element. Well, what is it that defines an element? Let's think of helium. We've got a relative atomic mass of 4, an atomic number of 2. What does that number tell us? It tells us how many protons there are, and that is critical to what element we've got. Okay, if you change the number of protons, you've got a different element. You can't change the number of protons without changing our element. So if we want the same element, we must have the same number of protons. We can change the number of neutrons. Okay, our relative atomic masses are made up of how many protons we've got added with our number of neutrons. Okay, we can change our number of neutrons as long as we don't mess with the number of protons. We've got the same element, and the only answer where the number of protons does not change is answer C. So there we go. Question 9. What have we got? We've got the most abundant form of radium is radium-226. Its nuclear mass is 226 and its nucleus contains 138 neutrons, which is an isotope of radium. There we go, 4 options. What do you know? Okay, so we've got radium, we've got the relative atomic mass of 226. Okay, what's our atomic number? Well, let's work it out. I've got 138 neutrons. Okay, and I know this number is going to be protons plus neutrons. Sorry, I'm thinking upside down. This number is protons plus neutrons. Okay, and this number is going to be protons only. Okay, so this is my total number of protons and neutrons added together. Okay, I can say that 226 is my total, is going to be made up of how many neutrons I've got added to the number of protons I've got. Okay, so what number do I need to put in here to add to that to make that? Okay, I can simply do 226 minus 138, and it's going to give me 88. So this number here would be 88. I've written the numbers around a different way because depending on which periodic table you've got, you need to remember it's not where the numbers are, it's the big one is the relative atomic mass, the small number is the atomic number. Okay, it depends what periodic table you're looking at. Okay, the relative atomic mass might be at the bottom, the atomic number might be at the bottom. So get used to the idea that the big number is the mass number. It makes sense, it's the bigger number because it's the one with both protons and neutrons in it. The small one only has the protons in it. Okay, so let's have a look at this actual question. What's it really asking us? It's got 4 options. We're talking about an isotope. Okay, so we mustn't change the number of protons. Okay, so the mass can change, the number of neutrons can change, but we need to make sure that we don't mess around with our number of protons. So what we can actually do is let's just work it out for each particular answer we've been given. Okay, let's have a look. What have we got? We've got A says we've got 226. If we take away the number of neutrons, it should give me okay, so the number of protons in this case is going to be 89. Well, that's not radium. Okay, I need to remember I'm aiming for 88 here. So it's not A. B says I've got 226. If I take off my neutrons, I get 87. Well, that's not radium. Okay, so that's not an isotope, radium. 227 minus 138 gives me too many protons. That's not radium. So it must be D. Let's have a check. It's 227 minus 139 neutrons gives me 88 protons. That is an isotope of radium. Okay, excellent. D. Sound wave travels from water into air. Its wavelength in air is longer than in water. What about the frequency and the speed of the wave in air compared with their values in water? Okay, so what do you think? Okay, so it tells us that the wavelength is larger in air. Okay, what about frequency? Now, frequency is related to pitch. If you're underwater and someone's shouting at you and you can hear sound, okay, the pitch of their voice hasn't changed. Okay, you might sound a little bit muffled, but the pitch itself hasn't changed. The frequency stays the same. Okay, we might have gone from a higher density to a lower density. Okay, it makes sense that something changes, but the frequency stays the same. Okay, V equals F times lambda. If frequency stays the same and wavelength gets larger, we're going to get a larger speed, aren't we? So if wavelength increases, okay, if you put a larger number in here, you don't change the frequency, you're going to get a larger number here. So we're going to expect a higher velocity. Okay, so let's have a look, see what we've got. We're looking for the same frequency, faster speed, C. Okay, check your answers. How did you do?